In this video, we will do an implementation of Heapify function in Haskell. And also, we will implement the removing the maximum element from the binary heap. How this works? For example, here they have the binary heap. And what if I want to, for example, remove some elements from this heap? I want to remove maximum element from it. Okay, maximum element here is 50, and then I remove it. When I remove it, they represent our binary heap as an array. So it started from this and so on, from top to bottom, from left to right. And when they remove this from here, we take the latest, the last element from the list. This is 1. They put 1 here. And now at the next step, they see its left and right children. So if sum of the children is greater than this element, then we must exchange with this element. So for example, here is their left and right children is greater than 1, and they replace our 1 with 40, and 1 goes here. And then they need to repeat our steps for this subtree. So here they see that 8 and 5 is greater than 1. This means that they exchange our 1 with 8, and 1 go here. And here they have nothing to go down, and they stop. So let's look the animation how this thing works. I will now press extract max, and they see all the steps about which I talk in this animation. Okay, and here is our new binary heap. We've removed a maximum element, and this was the intuition how it works. And now let's go to our Haskell code and implement this function. So here we see that our Heapify function started from here, and it was processed 2 times, here and here. Here I have some functions which was implemented in the previous video about insertion into the binary heap. You can see all this code. I will put link in description. And now we start to implement our Heapify function. Okay. Let's, as always, start from its type signature. I will call this function HP, and it take some binary heap represented as a list. Also, I need to have a pointer to the current element in which we do our Heapify, to the node, okay, in which we do our Heapify. And I need some flag which represent when they need to stop. Okay, and our function will produce exactly the same state, but with some exchange, swapping nodes in our binary heap, and the new pointer to the node in which we need to repeat our Heapify. And also it returns some flag that tell us then to stop. Okay, and I think I need to ord type class here constraint to A, because they compare our nodes. So let's start to implement this. I will enter match our triple here, and here we need some implementation. Also, I need some helper function here, which extracts the element from a list by its index. So let's skip our implementation, and I will reload this module. And now let's check. We have this access function to list by its index, but I think this function is not total. Okay, I can check this. Yes, you can see, but no, I didn't run it. You can see that it can have exceptions on some values, but I want the total function, and I will implement it like this. So it works exactly the same, but now I can, our program doesn't crash. So, okay, we can see that it works. Okay. Okay, how Heapify works. We already see this on the previous animation. We start from the root node of the tree. We take this root node and we compare it with the left subtree, with the left child and with the right child. Okay. So our left and right subchilds defined like this in our list. So I put this thing here. And here we have some possible ways. So if our current node is greater than the left and the right child, we can say that it's okay, it's a binary heap, and we can stop here iteration. But it's also possible that the left child is greater or the right child is greater. And also it is possible what we have not left and right child at all, or we have only one left or right child. And we need to handle all these cases. So let's start from some case. Then we have left element and right element. Okay, for example, what if they have both of them? And we need something to do with them. Okay, and let's define them. I will define it like here, like this. So left element, this is the element which we take from our list with our access by index operator with some index which I defined like this. Okay. And also we have a right element which defines this index. And also we need to define these indices. And these indices we defined like this, I think. We need to, for left child, we use this definition. And for right child, then you use this definition. So, oops. So I defined it here. Okay. Okay. But this is actually, this is not indices. This is markers of our nodes, which we see in our visualization. they started from 1, but in an array we start from 0, and they need to have some transformation for this. They need to subtract 1 from them. Okay, let's do this. Subtract 1 here and also subtract 1 here, and we have correct indices. Okay, and also we have index for our underscore mean index in this case. So we have the index for our current element, and we have our current element which we extract with this index. And I assume that our index is always correct. We put here always correct index. I didn't want to check this here with maybe type. Okay, we have these values here, left element and right element, and the problem is that this is maybe values. This means that it is possible that there is no value for them. And in this case, we need to stop our computation for the first case. And the first case which I want to check here if we have some element and our element is greater than left element and right element. And in this point, they need to stop our processing because all is done. The binary heap constraint is held. Okay. But as I said, it is possible that one of them is nothing or both of them is nothing. And I need to handle this case. This means that I need to use some, I can use some function which working with the lift m2 function, and this function is somehow penetrated inside our monads. We have two monads here, left element and right element is a maybe monad, and it needs to somehow to penetrate into these monads. And let's import some module for this. It's called import. It's called control.monad, I think. Okay. Where is my implementation here? So we using lift m2 function. Okay, I want to show its type signature. Let's look at this. Import control monad lift m2. So we have some penetration function here and two monads, and we produce the new monad. Okay, this is our monadic values, and I will use lift m2 here, and here I'll define some lambda function which takes these elements. And if they present if the values in these monads constructed with the just constructor, when we can extract them here. Otherwise, we will return nothing. And here, inside our function, what we do? We checking what we are in some case. The case is if the element is greater than left element or equal, and also element is greater or equal than the right element. Okay. So if this thing holds, this then means that we can stop our iteration and we return the triple as it is, but with the marker when we can stop. Okay, but otherwise we need to return nothing because they didn't catch this case, and we need to do some more checking here. Okay, and if I return nothing here, this means that I need to also return here maybe type, but I return in triple, and to wrap it into my maybe type I will use a just constructor. Okay, we have this thing here. Now here they will what will be the type of this expression? The type of this expression is maybe triple. Okay, and this means that I need to remove one extra layer of maybe with the join function. Okay, I will call this here. Okay. Okay, and this thing, this whole expression will give me maybe this triple if this case holds. Of course, if all the left and the right subchild presents in my list. Presents, I mean that there is nothing for one of them. But if there is nothing for one of them, and or this thing not holds, then we will receive nothing. And this means that we need to use some other catching case for our cases to represent our state of this triple, of new generate triple. And to catch this thing, we can use some very useful operator from control alternative module. Okay, I will import it here. Import control alternative. And this operator look like this. So let's look at its type signature. Import control alternative. Sorry, not alternative, I think applicative. I need to change it here and to use it here. Yes, and now I can look at type signature of this operator. Oh, it takes two alternatives and produce a new alternative. So in case of maybe, if my first alternative is broken, it returns nothing. If it returns nothing, it tries some other alternative. And this alternative will catch our second case. And what is our second case? In our second case, I want to catch some case, then we have then our current element is greater than left element or equal and less than right element. So let's write this thing here. Let's write it. So we change only one condition here, like this, I think. And now we need to, if they have, if this thing happens, we need to provide some new state here. And this state actually is constructed from a previous state with swapping some elements. And which elements this swapping? So if the element is greater or equal than the left element, this means that we need to swap the current element and the left element. Okay? And this will be one iteration of our Heapify algorithm. And to perform the swapping, we already have the function which called swap. This is function which I defined in a previous video about insertion. It's just do the swapping some elements in the list. And let's use it here. So we'll call swap. This swap them our current element. It has index I underscore, and we swap with it left element index. Okay, like this, I think. Like this. Of course, not like this and like this, because our right element is greater than the current element. This means that we need to exchange our right element with the element, and for left element it's less than our element. This means that it's the property of the binary heap holds for the left branch, and they need to go to the right branch, and they do this swapping here. And also, of course, we need to provide a list for this function, and they need to construct a triple for this. So this is the first element of our triple. The current element of the next step will be right element. Okay. Index. And of course we return false because we do some modification, some swapping, and maybe we need some more processing of our state. Okay. Yes, I think this thing should work. Yes, yes. Yes. And of course we doing join at the end because we have two layers of maybe here. Okay, but we have some more cases, and we need to catch this alternative here. Of course, second case is the symmetric case. So the previous case, if we have some element less than left element, and right tree is and all okay with the right subtree. In this case, we change it to left element here and go to left element. Okay. And let's go to the next case. What if we have left element and right element, both elements, and the left element is greater than the element, and the right element also is greater than our element? In this case, they need to select the maximum, the max element from left element and right element, and use it to exchange with our element. Okay, so here we need some additional checking. If our left element is greater than right element, then they need to do something, and otherwise they need to do something. Okay, if the biggest element is left element, which this means that they need to generate state like this. We change it to the left element and go to the left. And otherwise, of course, we need to, if right element is greater or equal, we will select going to the right element. Okay. Yes, I think this should work. Let's go to the next cases. Here they can handle all the cases if they have both left and right elements, but there is also possible case when they have only one of the left and right elements. Okay, and also it is possible that no left and right elements at all. Okay, for these cases, of course they need to use not leavEm2 function and just leavEm function. Okay, this is exactly like leavEm, but with a less number of arguments for our penetration function. And I will take it from here, I think, not, I think from here, in this case. Copy it to here, and here I will change it to leavEm, and what if I have only left element? And here I need to check if our element is less than, no, let's for example start from simple cases. If we greater or equal than left element, this means that they can stop here, so we can stay our state as it is, nothing to do, and we will put this expression here that represents this. Of course, and here I need to use only left element. So if all of these alternative broken, they try to use this alternative, okay, and so on. The next. So it's okay. The parentheses here, I think. Yes. The next case exactly the same. But they use right element. If we have only right element and our element is greater than our right element, greater or equal, we can return our state as it is without any modifications. Okay, but of course possible that have such a case if our element is less than left element. In this case, we need to do swapping with our left element, and I will take it from here. Okay. And Otherwise, if our element is gray or is less than the right element, well, they do swapping with the right element. Okay. Left element, right element, right element, left element, right element, right element. Okay. Okay. I think this all. Oh no. One last case. You have no left and right element. We need to return our state as it is because there is no possible to move down in our tree. And we return just our state. And they say what we can stop here. Okay, guys. Okay, let's comment here. No left and right elements. Okay. I think we can try to compile this thing and I will surprised if no errors here. Okay, let's try to reload. Of course. Some errors. Ooh. So I need to check my expressions. As I see, one thing I need to do in the end here, we will return just value of type maybe. And of course I need to extract it here because our type signature dictates me to return a triple, and this means that I need to use from just function here to extract my value. Okay, let's try to reload. Oh no. I see some logical errors here. So of course here I need to use these left and right element markers. Actually, there is no errors, just some verbose here. And why I use this $sign here? Let's remove it and reload. And I put this $signs here. I don't know, maybe I like dollars. Let's remove the thing. So, and here I think, and here. Okay, and from here, if I will remove, we have one last error and I need to fix it. I have a not left, so I use left right element here, not left. And we done. Okay. Now let's try to provide some iteration steps with our HP function. What if I have I will provide some heap, broken heap like this, for example. And I will start from 1. And I need to process. So I will run this thing and I will get the swept list and new current element. Okay. Of course I can process this thing again and this tells me that I can stop. Okay. So using this iteration function, we can now implement our final Heapify not Heapify. This is a Heapify function in one step. And using this, we can implement the extraction of the maximum element from our heap. And let's do it. Let's start from type signature. Okay, I will call this function emax. This means that extract the max. And we have some binary tree. And as a result, we need to produce a pair which contains the extracted element and a new heap without this element. Of course, I need to have some constraint for ordering our A values. And now let's do the implementation. They receive our list, and I think I need to so the maximum element, so I need to pattern match this list, and the first element, the head of this list, also is exactly the maximum element which they need to return. They need to construct a pair with the first element x and some new modified binary heap. Okay, binary heap. And they need to define this binary heap somehow. Our binary heap is something. Okay. And how can they define our list? Okay, they constructed without it with iterate. Of course, we use iterate function, and they need to provide here our function heapify. This is iterated process of heapifying, and they need some start state here. It's some list from which we take the last element and put it to the top. So I will call it LL now and define it later. And we start from the root, heapifying from the root, and we need some processing. Okay, and let's define this list. Let's define this list. We take the last element of XS and put it to the head of the list. And they need to take the image of this list and use it as a tail. So we construct it like this. And now we have this iteration process. Of course, we need to find some point in this iteration process, and we will use a find function for this, which takes some triple which we pattern match here. And we have some lambda in which I pattern match the state, and I need to find some flag, okay, and return this flag here. Okay. This expression will give to us the maybe. This expression will return the maybe triple value. This means that we need at first extract this from just, and then extract the first value from this triple, and we have this simple function here. I will use it. It just extract the first value of our triple. Okay. And I think this should work. Let's try to check. Thanks, it loads. Now to check this, I need to use some function which was implemented in the previous video about insertion. It's some helper function which allows me to build a binary tree from any list. It's called BFL. It takes some list and produce a binary tree. So let's run this function on some list. It can be any list with some values in any order, but at the result I will receive the correct binary heap. Okay, for example here, okay, I will print it. You can see this is a binary heap. It's correct binary heap. So it's complete binary tree at first, and at every node, all sub nodes are less or equal to this node. Okay, and now let's try to remove, for example, so I build this tree again, and now I will extract maximum from it. Yeah, max. BFL builds a tree for me. Okay. But I don't. Yes, of course. BFL. We have battery here, but I need. So I think I need some helper here, which just defined as this. So I will use folding for iteration of insertion of some lists, and I will call this function as build list. Build heap list as list. Okay, build heap as list. Okay, and it defined like this. So now if I reload and if I run this this function, this list, I will get the heap. You can see here we have somehow swapping our elements, which represents this heap as a list, as this list. And now, of course, I can extract the maximum element from it, and I will receive this element and the new heap. And now let's check that the let's take the second element of the new heap and print it. At first, of course, I need to transfer it to a tree with our helper function BFL. We will do this, and then I will print it. Okay, and you can see that this is new. Okay, new heap, correct heap with extracted 9. So we extract 9 from here, and our 3 goes here, and then it is moved to our tree here, and we build the correct binary heap. Okay. So guys, I think this we do our implementation of extract maximum value and the Heapify function. Of course, we can optimize this code to run it faster, not using the list. We can use some arrays or hash maps, maybe. Yes, we can use int hash map, for example, to get the faster access to our indices and fast swapping. Okay. But I think I'm not going to implement these optimizations. But if you want, please write in the comments, push like button, and subscribe, and tell me if you want this realization, this implementation, and I will implement it to make it faster. So thanks for watching, push like, push subscribe, and see you in the next video. Bye bye.